that's the point, that if we go in the evening, then you're allowed to get extra time. But then all of us have to agree for that. And it's usually harder to, at this point, if this is too late to think about an evening. Already Aryan has a conflict there. So let's not think about that. So it will be, unless all of you are available after this, this ends at 11 o'clock, like 10:50, this class. Is everyone available? No. So, so then so we stop at 10:50, like a little bit here and there. That's okay. So just to be fair to everyone, we stop at 10:50.
You can also shut down here instead of 9.
Ah, that's a good option. Is everyone available before 9:30? Is everyone available? Alia, you shook your head. You're available.
Hour, I mean.
Oh, you guys ask each other. 5 o'clock?
Not before 9.
So, okay, first let me ask, are you guys available before 9:30? Michael, are you available before 9:30 on Thursday for the exam?
Yeah.
So I will try to come here. I can start anytime. Now it's up to you guys. Now, when do you want to start? Who is the one who wants the earliest? I will come at that time and others can come later. You can start at 9:30 if you want. Or even 10 o'clock, who cares? Right, but it ends at 10:50.
I will throw a word of caution. The more time that you have, the more questions he may feel are necessary.
No, honestly, I will try to make it for 9:30 to 10:50. But you're right that could be a bias there. That extra time. Bias you cannot help. But I will not plan to make it longer. I try to make 4 questions in 75 minutes or so, like each one about 10 to 15 minutes. So that's I aim for. So yeah, or another way of arguing is that if you don't get the question in about one question in half an hour, probably you won't get it. It's unlikely if you're not able to begin it. If it is a mechanic, if it's too long a problem, then I understand. Usually the problems are not long. At least I would say it's not too long. So yeah, I think too long, like 5 o'clock is not necessary for sure. But half an hour can help. 1 hour can again help, but not more than that. Like a 1 hour exam, it should not take more than 2 hours. Then the exam is not good. It's not bad if a 1 hour exam takes more than 2 hours. So I suggest, how about this? So 9:30 is the usual time. I can be here at 8:30, right? And it's not compulsion for you guys. If you like to relax at the usual time and come at 9:30, come at 9:30. But I will be available at 8:30. Is that reasonable? Okay. It's up to you guys what time. But if no one is coming at 8:30, then I don't have to come. So you tell me. If yeah, I think it's just 1 day, so I don't mind coming in.
I'll try to be here at 9.
9. Okay. Is anyone going to be here at 8:30? Okay, you. Okay, so 8:30. So at least one person should be there. Otherwise, yeah, even otherwise it doesn't matter. I think 1 day.
I'm coming back tomorrow night because I don't like getting up at 5 o'clock in the morning and then taking an exam.
So you will be coming from?
I'll be actually in town.
You'll be in town, so you'll come
So I can
previously
pretty easily.
And we will cover everything that was covered until last lecture. But today's lecture is also very related. So in that sense, I would say it's not technically covered, officially covered, but it's very related. So I can change it a little bit. I did post a new homework. So this is due Actually, I should say midterm history. Oh, yeah, so this is, oh, did I record this? I think I have to change the camera. This is 8:30. Let me change this camera.
That'd be the 24th.
I planned to make it due Tuesday, and then I postponed it to Thursday. I guess I did not write that here. Maybe in the homework also it might show wrong. Right. Yeah, thanks. Yeah, 17. Yes. So our goal was from the beginning, we had an eye on the fact that Newton's law probably can be written as a minimization principle. And this is broadly called Hamilton's principle of stationary action. Sometimes it's called stationary action principle, or just principle of stationary action, or many like to say Hamilton's principle of stationary action. This is broadly what we say Lagrangian, whatever is studied as Lagrangian mechanics. That's what it is. Okay, so before that, we should review Newton's laws, right? Very quickly. It says rate of change of momentum, and momentum is mass times velocity. In general, it's a vector. It's a three-dimensional vector, so that's rate of change of momentum is equal to the sum of forces acting on it. We have vector relation, identify all the forces. If you have only conservative forces acting, if the forces are conservative, so that means that by if the forces are conservative, that means that all these forces can be written, let's say Fi can be written as a gradient of a potential energy. Let's say this is U of I. So this is potential energy. And there are very few forces that can satisfy this. Gravitational force is one, electrostatic, both electrostatic and or electromagnetic forces are an example. And in one dimension, spring force is also an example of that, or I should say, actually even in 3-dimension, when you have this Hooke's law, k times x as a vector, they also satisfy that. In general, you can have a lot of functions. You can define your potential energy and take the gradient and get an equivalent force in that form. But in a natural setup, we see only electrostatics and gravitational forces having that situation. If that is the case, then we have our equation. Then, right? If they are conservative, then we have d by dt of mass times velocity is equal to negative gradient of potential energy. And let me say u here is u1 plus u is u1 plus u2 plus so on. So there's a total potential if you want. That's Newton's law, right? So this is your statement. It's also good to see this as it's also good to write this as maybe. So it's also good to see this as d by dt. mv is the partial derivative with respect to velocity of half mv squared. It's a derivative with respect to velocity squared, 2 times that will give you exactly half times mv, and that's equal. And here gradient, since I'm now having a derivative with velocity, let me write that as derivative with position. It's a more standard, so I'm having gradient with respect to the variable r will be d by r, and gradient with respect to velocity v is d by dv. And my r looks very much like v. And that's your q. And if you were to define half mv squared as k, so that's kinetic energy is half mv squared. Then we have time derivative of partial derivative with velocity of k equal to partial derivative with position of u. That's if you want Newton's law in the presence of if you can confine yourself to conservative forces, that seems to be equivalent way of writing Newton's law. Can we do something about this? And this is probably once you see this and then you have a lot of experience in functional derivative, you feel that, oh, maybe this has some signatures of a minimization principle. So let's go ahead and do an exercise in functional derivatives. So any questions? as of now, that should be just standard Newton's laws. Okay. So now we go to functional derivative. A warm up. So this is functional derivative again, but this time we will keep it very general. So presuming that we have had a good bit of practice in functional derivative, let's, instead of talking in terms of specific problem, let's have a generic functional. Let me call that I, and let's say that's your x, and let me say it is one dimension. So and x here is x of t. The x is a function of time. Think of it as a position of a particle with respect to time. And let me say I have a functional, this is t1 to t2. Again, this we want to think of it as time, but as of now, this is just a mathematical problem. I have a functional which is dependent on a function x, and let's say t prime, and let's say I have, let me keep it as Lagrangian itself. So this is going to be L or any function. So we will call this a Lagrangian, but as of now, this is just arbitrary random function. And why not yi? I was thinking keep it very arbitrary. We will call this an action very soon, and we will use the letter W for that. So let's L is a function of position of the particle. This is one dimensional. And it also depends on velocity, d by dt of x of t. Notice the way you want to think of this, it is a derivative of the position. Right? Given a position, it determines that if you know the position of the particle as a function of time completely, then you know its velocity also. So the moment you know x, you know its derivative. So it's x is the fundamental quantity here. If I change x, where a functional, remember, talks about changing your x, that means that's what you will change. And the derivative will accordingly change. And it could also depend on time. And in general, when we are talking about Newtonian dynamics, we say it depends on position and velocity. You give me the position and velocity at one point, Newtonian dynamics will tell you the position and velocity at every other future point, right? So in that sense, that's your position and velocity. We will also sometimes say we'll get lazy and we'll just call it velocity v of t. But whenever we write v of t, it means it is a derivative of position. It's not a new variable. It is x is a dependent variable or independent variable, and velocity is just a way of denoting. I can go back for a moment and notice this is all three-dimensional. But if I remove the vector sign, then it all becomes one-dimensional, right? If I say r is x and this is your v, then d by dv of k and d by dx of u, all that works in one dimension also. So that's so we would like to see if this has some signatures in there. Okay, so this is arbitrary, any function. Let's see what happens if we make a variation and do a minimization of this w, and what will happen. We will call this, since I have actually given these letters, we will call this action. So when we say stationary action, that means action is what is going to be minimized, and this is going to be the Lagrangian. Quiz, what is the dimension of the action? I haven't told you what Lagrangian is, but if you go back to your usual Lagrangian definition, what's the dimension of the action? So the quiz is what is the dimension of the, by that I mean the units of action. That's just a simple quiz. Okay. So let's make a variation before anything we say that there is any minimization principle. We should know how this changes, right? So let's say x goes to, so x as a function of time, you make a variation and you say you change this to x of t plus a delta of x of t. Again, this is a together thing, right? That's a small variation in the function x of t. So if I had a plot as a function, so this is t, so that's your x of t, and delta of x of t is a small variation. It doesn't have to be oscillatory or anything, it's just a small variation. This is together, right? Delta x is a function of time. That's the way you want to read it. You add a small function, an arbitrary function, which is available at every point t. So you make that variation, and that's the idea of functional derivative. We see what is the variation in the action. So we would like to see what is the variation in the action. And that by definition is, definition by construction. Oh, I should have said this is t prime, right? So I meant all this is t prime, t prime, t prime. And this will be lost in t prime. So here the change will be the region x goes to x plus delta x, and just to avoid clutter, I have dropped the t dependence. But if you have sufficient space and you're good at not confusing yourself, you can write the t. That's good. There's more information. This is let me write this explicitly. So this is dx by dt. But I changed my x to delta x, so there is a second term there. So that's d by dt of delta x. Right? Derivative of x is x plus delta x. That's how it will change. So that's your change in this. T doesn't change t. Oh, I should be t prime, right? So t prime, and this is t prime. Clear? That's your change in the action. We would like to make this a small change. A small change means that I can tailor expand this. Like think of when we were taking the derivative, we just expand this, and whenever there is a delta x at the final point, there I have to identify a delta function. So see what I'll be doing. So this is wx plus delta x. So I'm going to expand this t1 to t2 dt prime, expand this out. That's a two variable expansion. So L, keep that original piece as it is, and let me write this as V and T. That's your V. Expand it around that point. And there are two places where I can expand, first variable and the second variable. So that's plus delta x. So let's say dl by dx times delta of x. Notice I'm bringing in this t prime at this point. So this is where, when I divide it out, that's where the delta function will sit. Plus, this is now derivative of L with respect to V. And that change is d by dt of dt prime of delta x of t prime. And rest of them are higher orders. Is that clear? Oh, come on. Anything else? That's it. Is it clear what I did in that expansion? If it's not, let me quickly, just in case. So if you have anytime a function f of let's say x plus a, you would say the expansion is f of x plus a times b f over bx, right? Or you can say a is on the right side, that's perfectly fine. That's your expansion if you have one variable. If you have two variables, as far as you restrict yourself to leading order, so that means to say a is small, and this is f of x comma y plus a times derivative of x plus b times derivative with respect to y, and so on. So that's clear. So this is x comma y. Okay, so that's what I've used. In principle, there will be a square, there will be combinations also, right? A, B, a square, B, all that, but we have said that all that is higher order. You're not interested in keeping that. Expectation is that in the limit, this small variation goes to 0, all the other terms will not contribute. Okay. That's your original action itself. So I can take it to the left-hand side and say that's change in W. So change in the action, which is x plus delta of x minus W of x. So that's your W itself. Take it to the left, and I know that that's equal to T1 to T2. Oh, didn't change them. T1 to T2 dt prime, and you have let me write delta x the front for a moment. Delta x, yeah, doesn't matter actually. Right, the same, no confusion. Partial derivative of L with respect to x, and delta of x as a function of t prime plus prime that's pretty much rewriting it, except for this term which I call n. Let's do the functional derivative now. We divide this by delta x, correct? That's what we would do. So that's equal to. But I would like to, there will be situations where we would like to leave this at this stage also. We don't really have to divide it. This will be called a variational statement, and this is actually a derivative statement. So this will be delta of x as a function of t, right? At time t. That's what we do. Then you get a point here, and you get a function here, and both are identified as delta functions. Right? This is T1 to T2, T prime. This is recognized as the delta functions plus T d by dt prime of delta function. Okay. After all your homeworks, I think this much should be clear. It's just that we have kept it very general. So this can be evaluated. These are delta functions. We know how to evaluate this, and it turns out to be action, variation in the action due to a small change in x is equal to L by dx. And now as a function of, this is all function of t now, plus, or not plus, right? There's a minus. So minus of d by dt of d L by dv. All evaluated at t, so that's hopefully understood when I say that's t. At this stage, if you were to set a minimization statement, so you would say if you set this to be 0, whatever that means, this is what if, right? If this is equal to 0, then we have, let me write this on the other side, right? So then we have a statement that d by dt of partial derivative of L with respect to this velocity v is equal to partial derivative of L with respect to x. And you will notice that there is some similarity here, right? You don't really see that k and u, but all these operations are there. It's just that this is not k, this is u, this is kinetic energy, that's potential energy. But otherwise, these operations have some structure in it, and you say, okay, what does that mean? Is that something you can do about it? So here, this was very generic. We tried to start from Newton's law and reach here. So let's do some specific examples where you can see this k and u coming up and getting together into what will be called as a Lagrangian. So let's think of an example, right? So our goal is, so since we see the similarity, so the question we can ask is, the question is, given equations of motion, that's Newton's law, given Newton's equation of motion, can we find a Lagrangian? Can we find a function L, right, that satisfies the Hamilton's principle of least action to give us the equation of motion. Can be worded better, I guess. You get that. So let's do this for a very simple problem, right? So example, let's say. The simplest problem is uniform gravity, right? You drop a ball, it should go down, and let's say that's your G. And when a ball is dropped and you don't give it a horizontal velocity, it's just a one-dimensional motion. So we don't really have to talk about vectors. But let me say that this is my Z, right? All the Z will be measured in the positive direction. And you would say Newton's law tells us that d by dt times mv, which is dz by dt, right? So v here is dz by dt, right? All the z is measured in the positive direction, and that's equal to mg, which is acting down, right? So it is minus mg. Right. And you would say, oh, but I'm interested in writing it in this form. So you would say this is minus d by dz of mgc, right? That's the potential energy if you notice in one-dimensional, like this is what we study, right? Gravitational potential energy in a uniform gravity on the surface of Earth is just mgz. As you go up, you're increasing your potential energy. So that's your equation of motion. And the question we are asking is, what is the Lagrangian for this? What's the Lagrangian for this? So you immediately look at this and you say that, oh, I want to compare it with this. Right? This is what I want to compare it with. So you go, you rewrite this equation again, and you say, okay, so let me write these equations together. So that's mv is equal. I want to write it like this. Right? So this is d by dz of minus mgz. And I compare it with that. So let me write them together here, d by dt of dl by dv is equal to dl by dz, right? That's your Hamilton, that's your, this is often called just whatever we derive here, these are generally called Euler Lagrange equations. It doesn't have, I mean, this is done in a one variable, but for vectors also it goes through immediately. So, if we just compare these two, we can see that dl by dv is mv up to a constant with respect to t. Right? So if you want bring in many constants, so this can have a c1. As far as there is no time in it, no, this is a total derivative, right? So no, so as far as this is, yeah, it cannot have any other difference. Yeah, so it's mv. What I mean is that you would think that this should be independent of time, but when you say f of x, comma v, comma t, notice this is explicit dependence. And there is this here, which is a function of t. That's implicit dependence. In the sense that when I'm taking a partial derivative of f, that hits only the explicit dependence. A total derivative of f, by definition, is going to hit all three, right? That is a t here. So a total derivative hit all the implicit and explicit. and partial derivative is only explicit. That's the definition of it. Partial derivative versus total derivative. And in this dy dt here is a total derivative. So since it's a total derivative, it cannot depend on x either. So there is a constant. So if you want, you can write a constant C1, which does not depend on either x, v, or t, because if it depends on any of those, then that will give you extra terms. So that's a constant there, but it is not dependent on x, v, and t. Okay, so that's your first statement. If it's a constant, you can ask for drop it, but let me keep it there. We also have dl over dz is equal to minus mgz. No, what did I say? No, sorry. This is not this, right? So this is d by dz of minus mgz. Okay, that's your statement. Like immediate reading out of this. What can you say here? If this is true, I can say that this implies that L, which is a function of z and v, and if you want t also, that's what we are looking for. But the derivative of L, so L seems to be almost this. So this is surely a solution. But then, since we are taking the derivative with respect to z, I could have another constant C2, which depends on v and it depends on t. Right? That's a possibility because always, whenever I take this derivative with respect to z, that doesn't contribute anything, right? So that satisfies that. Let's see, what can I say about here? If this is true, this implies that the Lagrangian is z, v, and t is equal to derivative of something is mv, so that's half mv squared. That seems to be a possibility. Plus, this is a constant which does not have any v, right? So I can have plus C1v, I suppose, right? I guess C1v. C1 does not depend on any parameters, so that's v. Plus, I can have C3. Now, derivative of something has to be only having velocity, so I have to be getting rid of velocity, so this can depend on z and t. So derivative of this quantity gives me mv, this gives me c1, and this will give me 0 because there is no velocity in. That's a possibility if you want, in general. Right. But without all those constants involved, and this seems to suggest that Lagrangian is not unique, but at least we have one solution in here. Okay, what can satisfy this? Now I need time derivative of something has to be equal to that. So it seems to be that C2v, I'll put this in here, and C3z, that's here, right? Whenever I'm looking at this, C3 can take this value and C2 can take that value, right? Including C1 v, and maybe at least one solution, not one solution is that that's half mv squared and plus, let me say, minus mgz, right? And apparently C1v, right? But choose your C1 to be 0. I chose C1 to be 0. Right? So that seems to be a solution, right? Not necessarily the only solution. It seems to be there are many solutions, especially with the C1v. That's an obvious thing. So this is a solution, right? A solution. And in terms of kinetic energy and potential energy, you say, this is nothing but K minus U. Not the sum, it's not the energy, but it is it is a subtraction of this. In fact, the way it is constructed, or the way it worked out in this very simple problem, is that K has only V in it, and U has only Z in it. That's very lucky. I mean, that seems to be too simple, straightforward in a sense. But it gives us insight as to how to go about a general problem. So this is an elementary problem, of course. It's like variables got separated, and then you ask, can you actually construct an L in general? Like this seems to give you kinetic energy and potential energy. Subtract of that, not even addition, and let's see if we can do this at a more general level. So we say that, okay, let's take a more complicated problem. Let's do this in 3 dimensions. And let's see if we can do this similarly in a more a reasonably more complicated place. And where do you see velocity dependent forces? Maybe I should ask you, give an example where you see velocity dependent forces and which is conservative. Forces that are velocity dependent and conservative. Or let's begin by velocity dependent forces.
Magnetic force.
Magnetic force, that's good. And that's electromagnetism, that's considered a fundamental force. That means it must be conservative, and let's see if we can actually do that for this. Usually drag forces also come into mind whenever it's velocity dependent, but they are not conservative. Except when you have small velocity, linear velocity, there is a Stokes law that comes in. So that has nice features in there that should be paid, one should pay some attention to that. But still, that is dissipative. Let's talk about magnetic case. And did I move my camera? So what's the equation of the, so then what we're going to solve, a charge, so electric charge in a electric field and magnetic field. Not necessarily uniform, general, right? Not necessarily uniform, let's keep it very general. Arbitrary electric and magnetic field, but it should satisfy Maxwell's equation. Right? That's a requirement. It satisfies Maxwell's equation. And what's the force equation for this? What's the equation of motion of a charge in an electric and magnetic field? Given electric and magnetic field?
E plus V.
Exactly, right? So if electric force is Q times E and magnetic force is Q times velocity across the magnetic field. And that's equal to what is that on the left hand side? Change in momentum over time. What is momentum? Let's say mv, right? That's what we know. So probably v. So that's yes.
The last term, K plus U. This what? Because U is minus mg.
No, u is plus, right? So remove this minus sign. Right? In gravity, if you say, remember, work done. So you have G acting downward, right? And you're moving up, right? Z is positive, right? So if you move up a distance D, work done is force dotted with distance is constant, right? So that's mg times z with a cosine of 180, that's -1. Right, so that's the work done, but potential energy is negative of the work done. So that's because you want to take it to the left-hand side and say that it depends only on the final minus initial. So change in potential energy is minus of the work done. So that's mg. If you want delta z, you move from z1 to z2, and then you identify u as mgz. With the choice that z is equal to 0 on the surface, somewhere that is 0. So at z equal to 0, u is equal to 0. That's a choice. Right, so there's some intricate steps. Yeah. So in that sense, yeah, so this is k minus u. It would have been nice if it was k plus u, then you would say it's energy. That's a nice interpretation that energy is being minimized. It is generically true, like the system always tries to minimize its energy. That's what the system, it doesn't try to minimize the Lagrangian, but as an action principle, it tries to minimize the action. Yeah, but when we think of it on a daily, like as a principle, then energy is what is minimized. And we'll see that this can be, this is a Lagrangian. We will write a Hamiltonian for this. Hamiltonian in many situations, basically when time is it, there is no time in there, that will be interpreted as the energy, and that will be k plus u. So Hamiltonian is the k plus u there. Okay, so I think that's yeah, quiz, right? Maybe since you guys asked k minus u, quiz, let's say quiz is go back and review your thermodynamics. Right, and tell me what's the expression for free energy? What's an expression for enthalpy? Helmholtz free energy. These are all expressions you come across in your thermodynamics. And the question is, which one of this is related to your Lagrangian? Which one is most probably, most analogy-wise, right? Of course, you cannot say that the Lagrangian, but one of this can be associated with the Lagrangian, and then you can talk in terms of energy. So which one of this is energy? I mean, what else is that? Free energy, and what is U called in thermodynamics? dq, right? dq is heat, and that is dq and du. That what they call free energy is.
Sometimes it's eternal.
Internal energy, I think that's yeah, U, I think so. That's an internal energy also problem. Yeah. So maybe check it out. Yeah. Like there are these conversions you talk about. And what's the connection here? That is a direct connection we will see. And maybe a keyword also is look up Legendre transformation. Probably it's a little early, like in the next class, this is a more appropriate question. The idea is that if you make a Legendre transformation on any of this, one after the other, you get new ones. So you can start, I can start from the Lagrangian, make a Legendre transformation, get the Hamiltonian. Again, do a Legendre transformation, I get another one. So I can keep doing this here also. And that's the same idea you do in thermodynamics also. So it's a good thing to connect with. That's for your broader picture. Okay.
Is this for the next session or next Tuesday?
Oh, yeah, on the exam day, let's not have a quiz due. Yeah, that will be, yeah, during the next class, yeah. Okay, so that's your equation of motion. And we have to again write this as, so our goal should be to write this in this form, right? d by dt of this time dl, this is now in 3 dimensions. So that is a vector. I want a Lagrangian whose derivative with respect to velocity is mv, and whose derivative with respect to position, right? So let me write that as r. Right, r. Where did that go? That's behind this one layer down. And L. So somehow I should find a Lagrangian which gives me the above equation. So the idea is that, okay, let's go back here. And we have this Maxwell's equation. Let's actually use the idea that there is a gauge dependence in here. So let's yeah. I say gauge dependence. Notice that even I just now when I was saying the potential energy, it's only the change in potential, you know. You never know the potential itself. So you always want a reference point that z equal to 0, the potential is 0. So in that spirit, you know that the electric field is also can be written in terms of electric potential, that's gradient of an electric potential, and magnetic field is equal to del cross A. That's a scalar potential, that's a vector potential. Magnetic field is given in terms of a vector potential. Electric field is given in terms of a scalar potential. Is something missing in there? Very generically. Dynamics, yes, and that would be, yes, dynamics is missing, very correct. Electrostatics gives you electric potential, gives you electric field, but we are missing a time derivative here. If we are having dynamics more generally, it is the A by T, and that's coming from Maxwell's equation. That's almost a few steps from Maxwell's equation. Again, a quiz if you want. Yeah, let me not write it down. If you want, you can try to derive this from Maxwell's equation. Somewhere near ENM, you should have done that, or you will do that in your ENM. Okay. Any questions on this? Little bit, you're familiar with electric potential and vector potential. Hopefully, this is what is voltage, right? When we say electric voltage, that's a voltage, and this is the magnetic. You don't want to say voltage, yeah, magnetic potential also. Okay, so if that's the case, put this in there, and we should. So our goal is to write this as a gradient, right? So this is, we want to write something like this. This is probably already there. So we want to, our goal is to write this whole thing as a gradient. Remember, force is gradient of energy, right? So can we identify this energy for this whole system? That's what we are trying to do. So let's write this as a gradient. This is already a gradient, but all this is not. So let's try how much we can do. That's mv is equal to q. Substitute this. So this is so I'm putting it there, right? So this is gradient of minus Q phi. Q times minus of phi. And put that in parentheses, and that is this also. So it is minus of Q times partial derivative of time with respect to A. And I have your plus Q times V crossed with L. That's just writing your equations of motion in terms of potentials, electric potential, and if I multiply by Q, it becomes potential energy in principle. That's a cross product. We know how to deal with that. Let's expand that. That's gradient minus Q phi. Only one piece is coming as a gradient yet, right? You're very far away from what we want. Everything else is not at all like a gradient, but let's see what we can do. So this is minus Q, partial derivative with respect to time of A. And here we have plus, remember A cross B cross C is your back cap. So this is B is your vector. And remember B, I should be careful with taking this into the derivative. So let me write this as A and C, right? This is actually dot product minus of AB times C. This is actually A dotted with C, but if I want to write it as A dotted with C, I have to cross this into the B. But if it's a derivative, I should be careful, right? So I have to keep it outside. But now then I said that, oh, this is velocity. Like velocity does not actually depend on the gradient, right? It doesn't depend on a coordinate. Velocity is the property of a particle that depends only on where the particle is. It is not going to depend on a field variable. I can actually take this in, and then you see that, oh, so then I can write this as actually gradient of Q times V started with A. I took this velocity inside the gradient because velocity does not depend on the gradient or on X, on position, and then minus, and then there is A that's free, so that's Q times V after the gradient of A. Okay. That's clear. That's just a vector product I used. And you see the I see the gradient here. And whatever doesn't have a gradient, let me take it to the left-hand side. It seems like there's a time derivative there, right? So let me take it to the left-hand side. MV plus, this is partial derivative, notice. A. And let me take this also in here and write this as V is d, this is dx by dt, or position, right? X by dt dotted with the gradient of Q times A. That seems to be a single operator, right? And that's equal to the gradient. Let me pull out a negative sign so that I can identify it as an energy. That's negative gradient of Q times phi. That's the potential energy, electrostatic potential energy. And that is Q minus Q V dotted with A. And that's here. What is this? This is actually the magnetostatic potential energy. This is your current J, and that's your dotted with A. So that's a magnetostatic static potential energy. Notice it comes with a negative sign. What does that mean? The negative sign in there, the meaning is that here like charges repel, but in magnetostatics, like currents, if you have currents in the same direction, they attract, right? That's that opposite sign telling you that. So that's magnetostatic energy between two currents, where current is QV, right? That's it, current. This is the magnetostatic energy between Q and the potential due to other charges. This is the magnetostatic energy between a current and the potential due to other currents. But it comes up with this all this extra piece here, which I moved it to the left-hand side. But what is that equal to? Let's see this operator. Let me move the camera a bit there. That operator, d by dt plus dx by dt, or position, right? Or x and r are the same, times gradient, which can be written as d by dx, right? In my, this is not common. That's a gradient, right? What is that equal to? And this is operating on some function f. What is that equal to? Total time derivative, right? So, and it is important that this depends only on position, not on velocity. If this depends only on position, and it can depend on time also, then this is nothing but the total time derivative. Very good. Right? Because then I can hit on t or on the t inside of the x, and that gives you the chain rule. But it's necessary that it depends only on the position and not on the velocity. If it depended on velocity, then there will be another term, which we don't have here. So it is important that the vector potential that we discuss in electromagnetism is a position dependent quantity. It is not a velocity dependent quantity. If you identify that, that's a whole total derivative. That's really nice, because then we say that time derivative of mv plus q of a, and just to clarify, this is r of t, right? There's only position dependence in there. That's just to signify that. And that's equal to negative gradient of, oh, did I move the camera? Did not. 8, no, 6. Q times 5 minus q times v divided with 8, which is r dependent, only position dependent. All this so that we can rewrite our equations in this form. But this is an important thing in electromagnetism. It tells you that it is not just when you have magnetism or when you have dynamics, it's not just the energy, there is a momentum also is not usual, right? This is called the canonical momentum. This whole thing is called the canonical momentum, and this is what is defined as P. This is what is defined as the momentum, but it's not mv. Notice in electrodynamics, whenever things are moving, momentum is not mass times velocity. There is a momentum contribution from the potential also, which is very non-trivial. It has significant effects that even, yeah, I think we will have time to talk about that. We will talk about commutation relation of velocity, and it will not be 0. Okay, so in the last 3 minutes, at least I can identify something. So if this is the case, then I want to compare this with the Lagrangian, right? So I want to compare this and this equation here. It won't show up there, I guess, right? But is that visible at that grazing angle? Yes. So in that case, we can recognize that derivative with respect to velocity is equal to mass times velocity plus Q times A. Right, that's fine. Same idea as here. And there is some constant C1 and out, but let's at least get this. There's this again, I can do that constant, but let me keep it simple. And do the same idea here. Lagrangian here, dl by dx is equal to minus q phi plus q v dotted with a. And let me stop here and an exercise quiz again. Find L, right? Quiz. Just as a challenge, find L. I'll do this next time. Find L.
This is what with respect to R.
Yeah, I have been interchanging R and X. Yeah, right. Yeah. I have been interchanging R and X here, so this should be R or X. I've been freely doing that bad habit. So yeah, somewhere I wrote out that this is X. Yeah. But yeah, correct. It should be R. So let's stick to position in R and velocity is Q. So find L, right? That's the, it's almost there. We will go that side. So it will come here dotted with this, and then that's already there. It's almost there. We just want to put that. Okay. Thank you. I'll stop here, and we will have an exam on Thursday. Oh, Thursday, yeah, early morning. Right? I should remember to be here, right? That's a dangerous thing. If I, yeah. I should put an alarm. Thank you. Oh, I didn't change that.